Did you know that the universe is expanding faster than the speed of light? That's right, the very fabric of space-time is stretching at an astonishing rate. And that's just the tip of the cosmic iceberg. We're about to embark on a journey to explore the most mind-blowing facts about our universe, from the incomprehensible vastness of space to the bizarre objects that lurk within it. Prepare to have your mind blown wide open. Over the next few chapters, we'll uncover the secrets of black holes, dark matter, and even the possibility of a holographic universe. We'll delve into the mysteries of the Big Bang and explore the idea that our universe may be just one of many. Stay tuned as we reveal 10 universe facts that will leave you questioning everything you thought you knew about reality. Comment below with your favorite fact, and don't forget to subscribe for more mind-blowing content. The universe is constantly expanding, pushing the boundaries of space and time outwards. Imagine a balloon with dots drawn on it. As you inflate the balloon, the dots move further apart. That's a simple way to visualize the expansion of the universe. But here's the kicker. The universe's expansion isn't constant, it's accelerating. Like a runaway train, the universe is gaining speed, driven by a mysterious force we call dark energy. This acceleration has profound implications for the future of the cosmos. As the universe continues to expand at an ever-increasing rate, galaxies will be pushed further apart, eventually becoming isolated islands in the vast cosmic ocean. And as the universe expands, it also cools, leading to a state of maximum entropy where everything is spread out and energy is evenly distributed. A rather bleak end to our cosmic story. Our universe is home to a mind-boggling number of stars. In fact, there are more stars in the observable universe than there are grains of sand on all the beaches on Earth. Think about that for a moment. Every single grain of sand on every beach, and then multiply that by, well, a lot. That's the scale we're talking about. The sheer scale of the universe is enough to make even the most imaginative mind reel. It's a humbling thought, realizing just how small we are in the grand scheme of things. And yet, amidst this vast cosmic ocean, we find ourselves on a tiny blue planet, contemplating the wonders of the cosmos. Black holes. Just the name itself conjures images of cosmic abysses, regions of space-time where gravity reigns supreme. These enigmatic objects are born from the death throes of massive stars, collapsing under their own weight until even light itself cannot escape their grasp. But black holes are much more than just cosmic vacuum cleaners. They are profound distortions in the fabric of space-time, altering the very essence of how we perceive time itself. Imagine, if you will, approaching the event horizon, the point of no return. As you draw nearer, gravity's grip tightens, its influence becoming increasingly dominant. Time for you begins to slow down relative to an observer farther away. Your clock ticks slower, light stretches, and the universe around you seems to warp and distort. This isn't science fiction, my friends, but a consequence of Einstein's general relativity. Time, once thought to be absolute and unchanging, becomes fluid and malleable in the presence of these gravitational behemoths. When we gaze up at the night sky, we're treated to a breathtaking tapestry of stars, planets, and distant galaxies. Each point of light tells a story, a tale of cosmic events that have unfolded over billions of years. The night sky is not just a static picture, it's a dynamic, ever-changing canvas that reflects the vastness and complexity of the universe. But this view, as awe-inspiring as it is, represents just a tiny fraction of what's out there. The universe is unimaginably vast, stretching far beyond what our eyes can see or our instruments can detect. The stars and galaxies we observe are merely the tip of the cosmic iceberg. We are limited, you see, by the very nature of light itself. Light travels at a finite speed, and this speed sets a boundary on how far we can see. The light from distant objects takes time to reach us, and thus we are always looking into the past. The universe, as we know, has a finite age, roughly 13.8 billion years. This age is a measure of the time that has passed since the Big Bang, the event that marked the beginning of our universe. Over these billions of years, the universe has expanded and evolved, giving rise to the galaxies, stars, and planets we see today. This means that the light from the most distant objects has only had a finite amount of time to reach us. The farther away an object is, the longer its light has been traveling and the older the universe was when that light began its journey. Our cosmic horizon, the edge of the observable universe, is defined by this limit. Beyond this horizon lies a realm we cannot see, a part of the universe that remains hidden from our view. Imagine a vast expanding sphere with us at its center. This sphere represents the observable universe, the region of space from which light has had time to reach us since the beginning of the cosmos. The farther out we look, the farther back in time we see. Each layer of the universe we observe corresponds to a different epoch in its history, a different chapter in the cosmic story. The faintest glimmers we detect from the most distant galaxies are echoes from a universe still in its infancy. These ancient photons have traveled across the vast expanse of space, carrying with them the secrets of the early universe. We are, in essence, time travelers, peering back through billions of years of cosmic history with every observation we make. Each photon of light we capture is a messenger from the past, a glimpse into the universe as it once was. And yet this visible universe is only a small portion of the whole. Beyond the observable lies the unobservable, a vast expanse that remains forever out of our reach. The true scale of the universe is beyond our comprehension, a reminder of the infinite wonders that await our discovery. We often think of ourselves as inhabiting a universe dominated by stars, planets, and galaxies. And while these celestial objects are indeed impressive, they account for a surprisingly small fraction of the universe's total mass and energy. The vast majority, it turns out, is something we can't even see. We call it dark matter. Astronomers first stumbled upon this cosmic puzzle while studying the rotation of galaxies. The stars in these swirling cosmic islands were moving far too fast for the visible matter alone to hold them together. Something unseen, something massive, was providing the extra gravitational glue. This missing mass, this invisible scaffolding, is what we now call dark matter. It doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Yet its gravitational influence is undeniable, shaping the structure and evolution of the universe on a grand scale. But what is dark matter? That, my friends, remains one of the biggest unsolved mysteries in modern astrophysics. So, we've talked about black holes, those cosmic gluttons that consume everything that ventures too close. These enigmatic entities are formed when massive stars collapse under their own gravity, creating a point of infinite density known as a singularity. Anything that crosses the event horizon, the boundary around a black hole, is doomed to be pulled in, never to escape. But black holes are just one of the many fascinating endpoints of stellar evolution. But black holes aren't the only bizarre endpoints of stellar evolution. Stars, those brilliant beacons of light in our night sky, have various fates depending on their mass and composition. Some stars end their lives as white dwarfs, slowly cooling remnants of once vibrant stars. Others, much more massive, have far more dramatic conclusions. Let me introduce you to their equally strange cousins, neutron stars. These stellar remnants are born from the explosive deaths of massive stars known as supernovae. When a star with a mass between 8 and 20 times that of our Sun reaches the end of its life, it undergoes a catastrophic collapse, leading to the formation of a neutron star. Imagine taking all the mass of our Sun, a star that spans 1 million miles across, and squeezing it down to the size of a city, say Manhattan. This is not just a thought experiment, it's the reality of a neutron star's extreme density. The gravitational forces at play are so immense that they crush protons and electrons together to form neutrons. That's the extreme density of a neutron star. To put it into perspective, a single cubic centimeter of neutron star material, roughly the size of a sugar cube, would weigh about 1 billion tons on Earth. This density is so extreme that it warps the very fabric of space-time around it. These incredible objects are the remnants of massive stars that have gone supernova. A supernova is one of the most energetic events in the universe, briefly outshining entire galaxies and releasing more energy in a few seconds than our Sun will emit in its entire 10 billion year lifetime. When these stars exhaust their nuclear fuel, they can no longer resist the relentless inward pull of gravity. The core collapses under its own weight, and the outer layers are blasted into space, leaving behind a dense core that becomes a neutron star. The core collapses, and protons and electrons are forced to merge, forming a sea of neutrons. This process happens in a fraction of a second, creating a neutron star with a density so high that it defies our everyday understanding of matter. This neutron soup is packed so tightly that a teaspoonful would weigh billions of tons on Earth. Imagine holding a spoonful of material that weighs more than all the cars on Earth combined. It's a mind-boggling concept that highlights the extreme conditions in these stellar remnants. Neutron stars are not only incredibly dense, but they can also spin at mind-boggling speeds. Some neutron stars, known as pulsars, rotate hundreds of times per second. This rapid rotation is a remnant of the star's original angular momentum, conserved and amplified as the star's core collapses. Some rotate hundreds of times per second, spewing out beams of radiation from their magnetic poles. These beams are incredibly powerful, and as the neutron star spins, they sweep across space like the beams of a lighthouse. These beams sweep across the cosmos like cosmic lighthouses. If Earth happens to lie in the path of these beams, we see them as pulsars, rapidly flashing objects that were once mistaken for alien signals. The regularity of their pulses makes them some of the most precise clocks in the universe. If Earth happens to lie in the path of these beams, we see them as pulsars, rapidly flashing objects that were once mistaken for alien signals. These pulsars can help astronomers study the interstellar medium, test the laws of physics under extreme conditions, and even search for gravitational waves. The study of neutron stars and pulsars continues to reveal the incredible complexity and beauty of our universe. We humans, we love a good mystery, and the universe, being the ultimate mystery box, never disappoints. Consider this. What if I told you that everything we see, everything we touch, even ourselves, might be nothing more than a projection of information stored on a distant two-dimensional surface? Sounds like something out of a science fiction movie, right? Well, this mind-bending concept is at the heart of the holographic principle, a theory that attempts to reconcile the seemingly incompatible worlds of quantum mechanics and general relativity. Just as a hologram can encode a three-dimensional image on a two-dimensional surface, the holographic principle suggests that the information content of our three-dimensional universe might be encoded on a distant two-dimensional boundary. Think of it like this. Imagine watching a three-dimensional movie. You experience depth and dimension, but it all originates from a flat two-dimensional screen. The holographic principle proposes that our universe might operate in a similar way, with all its information projected from a lower dimensional boundary. We've all gazed up at the night sky and wondered about those twinkling points of light, each a distant sun, perhaps with its own retinue of planets. These stars, scattered across the vast canvas of the universe, have always sparked our curiosity and imagination. They remind us of the infinite possibilities that lie beyond our own world, each star a beacon of mystery and wonder. But what if I told you that out there in the vast expanse between the stars there are planets that wander alone, unbound to any star? These solitary travelers, known as rogue planets, drift through the cosmos without the gravitational anchor of a sun. They are the wanderers of the universe, moving silently through the interstellar void. These are the rogue planets, cosmic nomads adrift in the interstellar void. Unlike the planets in our solar system, which orbit the sun in a predictable dance, rogue planets follow no such path. They are free agents, moving through space with no fixed destination, their journeys dictated by the gravitational forces they encounter. These planets are thought to have formed in the same way as planets in our own solar system, within the swirling disks of gas and dust that surround young stars. In these protoplanetary disks, particles collide and stick together, gradually building up into larger bodies. Over millions of years, these bodies can grow into fully fledged planets, each with its own unique characteristics and potential for hosting life. However, gravitational interactions with other planets or passing stars can fling these planets out of their stellar nurseries, casting them out into the darkness. These interactions can be violent and chaotic, with planets being ejected at high speeds, sent hurtling into the interstellar void. Once free from their parent stars, these rogue planets embark on a lonely journey through the cosmos. Imagine the view from such a planet, a world perpetually shrouded in darkness, illuminated only by the faint glow of distant stars. The night sky would be a tapestry of tiny, cold lights offering little warmth or comfort. The surface of the planet would be a desolate, frozen wasteland, with temperatures plunging to unimaginable lows. With no sun to warm its surface, a rogue planet would be an incredibly cold and desolate place. The lack of sunlight would mean no seasons, no day-night cycle, just an endless, unchanging night. The surface would be covered in ice and rock, with any atmosphere likely to be thin and inhospitable. But even in this cosmic isolation, these planets could still hold the potential for life. Deep beneath the frozen surface, geothermal activity could create pockets of warmth, providing the conditions necessary for life to exist. These hidden oases could harbor microbial life, thriving in the darkness, far from the light of any star. The discovery of such life would be a profound reminder of the resilience and adaptability of life, capable of surviving even in the most extreme and unlikely environments. The Big Bang. It's a catchy name, evocative of some colossal detonation that birthed our universe. But the truth, as always, is far more nuanced, far more elegant. You see, the Big Bang wasn't an explosion in the traditional sense, like dynamite on a demolition site. It wasn't matter bursting into a pre-existing space. Imagine instead, if you will, a universe infinitely smaller than the smallest atom, unimaginably hot and dense. This wasn't an explosion of matter, but of space itself. Imagine a tiny balloon suddenly inflating, expanding rapidly in every direction at once. That's closer to the mark. This expansion, this stretching of space-time continues to this day. Galaxies aren't flying away from each other through space. They're being carried along by the expansion of space itself. From our vantage point here on this pale blue dot, it's tempting to see ourselves as the center of it all. Throughout history, different cultures have placed Earth at the heart of their cosmology. But our understanding of the universe has evolved, and we now know that there's no privileged location, no cosmic address that marks the center of everything. Think back to that expanding balloon analogy. Every dot on its surface, representing a galaxy, is moving away from every other dot. But there's no single point on the surface that you can point to and say that's the center, the origin point of the expansion. The expansion is happening everywhere at once, equally. And it's the same with our universe. No matter which galaxy you're in, every other galaxy appears to be receding from you. It's a property of the expansion itself, not of any specific location. From the mind-bending expansion of space-time to the unfathomable density of neutron stars, we've journeyed through just a handful of the universe's most incredible wonders. It's a humbling experience, realizing just how much we still don't know, how much there is left to explore. But that's the beauty of science, isn't it? It's about embracing the unknown, asking the big questions, and constantly pushing the boundaries of our understanding. The universe is a vast and mysterious place, full of awe-inspiring phenomena that challenge our perceptions and ignite our imaginations. If these facts blew your mind, make sure to hit that subscribe button and share this video with your friends. Let's explore the mysteries of the universe together. Which fact surprised you the most? Let us know in the comments below.